Hey everyone, welcome back, and today let's solve Leetcode problem 2226 titled Maximum Candies Allocated to K Children. So it is a pretty long problem statement, at least relatively. On a high level, essentially what they're saying is that we're given an integer array candies, where candies at index I is going to represent the number of candies in the ith bag, and we also have an input integer k that's going to represent the number of children. And our task is very simply to determine the maximum number of candies that each child can get equally, while also ensuring that all of the k children get the same amount, right? So let's go ahead and look at some of these examples here. In example 1, we have our input array candies to be 5, 8, 6, and we have k to be 3. What k to be 3 really means is that we have 3 children, and we have 3 different bags of candy, each having 5, 8, and 6 candies respectively. Now, the reason why our output is 5 is because that is the maximum number of candies that we can give each of the 3 children without actually exceeding the amount of candies we have throughout all the bags of candies, right? And the way we can do that is we could divide candies at index 1 into 2 piles of 5 and 3, right? So this would be 5 plus 3, 8. And then candies at index 2 is a 6. We can break that into 5 and 1, right? And then we can allocate these 5 candies for the other child, and so it is guaranteed that we actually do have, or it is proven that each child cannot receive more than 5 candies, right, for these 3 children, right? And we have this very similar explanation here, right? We have 5 piles of candies of sizes 5, 5, 3, 5, and 1. In example 2, we have our input array candies to be 2, 5, and k to be 11. In this case, we really only have 7 candies as a whole. We have the first bag having 2 candies and the second bag having 5 candies. K in this case is 11. We have 7 candies, but 11 children. Each children can't even get 1 candy at minimum, right? Because we have more children than we do total candies throughout all the bags. And so nobody can get, or we could have 7 children get 1 candy each, but then 4 children would not get any candies. That is not allowed. We want the maximum number of candies that each child can get, where each child has an equal number of candies, and so we have to have an output of 0, right? Just giving all the children 0 candies. So for our constraint series, that the length of the input array candies is not going to exceed 10 to the 5th power. Any value in the candies input array is not going to exceed 10 to the 7th power, and the k value itself for the number of children we have is not going to exceed 10 to the 12th power, which are pretty large numbers in terms of problem constraints. And it tells us that, okay, we can't have a linear time solution. Why can't we have a linear time solution? Well, because we have very large values for the constraints, 10 to the 12th power, and so it kind of tells us, okay, we should probably kind of have something logarithmic, right? Which brings us to the main observation that we should really make to help solve this problem efficiently, right? If we fix, and kind of just leading to that observation, what is the main observation? Well, if we actually fix an amount, let's just call it x, of candies per child, we can then check, okay, is it actually possible to allocate those x candies in a way that all k children get exactly x candies each? If x is too high, we won't have enough candies to distribute. We have to decrease our potential x value. However, if x is too low, we can easily do it. Well, let's just keep trying to increase x until we get a higher valid allocation, until we can't go any higher. Now, what does that remind you of? Well, that is a standard template for the binary search algorithm. Also very ideal because, like we talked about a couple minutes ago, we want something to be a logarithmic algorithm because we are given 10 to the 12 for our problem constraints. That is a very large input, and so we can't have a linear time solution. We would get a TLE, and so this is a classic binary search algorithm or implementation, right? Our answer would lie in the given range from 1 to the maximum of candies, right? If we exceed maximum of candies, it would be redundant because it wouldn't really help or contribute any more to our solution, and we can actually use the binary search to actually efficiently determine the maximum valid x without actually having too many candies for an invalid kind of reach or threshold to pass all k children to get equal candies, right? So on a high level rundown, how is our solution going to look? Effectively, the lower bound, kind of like initializing the search range, the lower bound would be 1. That is the minimum valid allocation per child. It would be at least 1 because each child can get at minimum 1 candy. And the upper bound would be, like the high bound, it would be the maximum of the candies, right? Because the maximum number of candies that one child could get is from the biggest pile, right? And so for the actual binary search for the optimal candy allocation implementation, we're always going to try a middle value in each iteration of the binary search. It's going to be low plus high integer divided by 2. That's going to be the current possible number of candies per child that we'd be checking if it's valid or not in the current iteration of the binary search implementation. And we can then check, can we actually distribute those mid candies per child to all the k children equally? If it's possible, great, we can increase mid, try a larger value, and so we can set low to be mid plus 1, increasing the range. However, if it isn't, we can set high to be mid plus 1, decreasing the range, so we have smaller values to check from. And to actually check if they're all actually feasible, to basically check if any valid or any value mid is actually a valid allocation, all we can do is really just iterate through the candies array and count how many children we can actually satisfy with mid candies each. If the total number of children we can satisfy is greater than or equal to k, perfect, the mid is actually a valid allocation. If it's less than k, that means we have too many children, it wouldn't be valid, and so we'd have to try a lower value for mid. And the maximum valid mid value that we find through the entire binary search would be our resulting answer. So let's go ahead and get into the problem here. So I actually have a quick base case that I kind of didn't really gloss over in these high-level rundown. What if k is 0? Well, if we have 0 children, well, then we don't have to distribute any candies to anyone because there's no one to distribute to. There are no children. No one needs to even be distributed to. We just return 0. Very simply, a nice little quick base case. And now let's actually initialize our binary search range. And like we talked about, we'd be using 2 pointers, high and low. Low would be initialized to 1. Why? Because it's the minimum number of candies that any children can have. And high value would be starting off at the max of candies. It's going to be the biggest pile, right? Now let's actually get a quick helper function in here. I'm going to call canAllocate. This is where we're actually going to be using this mini function to actually check if a certain mid candies is actually feasible or not in a very quick fashion. So it's going to have one parameter mid. And I could type hint this, but I'm not going to. It's going to have a Boolean output, and it's going to take an integer mid, right? This is really just, again, going to check whether it's actually possible to give each child mid candies, and we actually calculate mid in each iteration of the binary search, meaning low plus high divided by 2, right? And now let's actually get kind of define this canAllocate function. Basically, it's going to be, we're going to initialize a count. It's going to be the sum of C, and I'm going to use something called list comprehension here in Python. It's just, basically, it's just a for loop in one line. It's going to be C, integer divided by mid for all C in the candies, right? Basically, we're iterating through each pile, or C, in the candies, and we're going to divide it by mid to actually count how many full mid-sized positions or portions we could make. And then we simply just sum up these counts, and we then determine the total number of children who can receive mid candies each, right? So, and the way we can really check that is quick. Okay, we have to return if the count is actually greater than or equal to k. If it's greater than or equal to k, we can accommodate at least k children. It's true, perfect. It means mid is a feasible allocation. If it isn't, though, we cannot allocate or satisfy that many children, and so it would be false, right? So this is basically checking if we can actually allocate this number of candies mid, which we'll calculate in every iteration of the binary search implementation. So now let's actually initialize our result. As you may imagine, this is going to be our resulting output or answer. This is going to store the maximum valid candy allocation, basically the maximum mid value that we find throughout all the iterations or calls in this while loop here for the binary search. And that brings us to what while loop we'll actually be using. Very standardly for all binary search implementations, we always have while low is in bounds or less than or equal to high. This is the actual binary search loop. So while low is actually less than or equal to high, while those 2 pointers are in bounds of each other, we'll calculate the minimum value in each iteration of this binary search. It's going to be low plus high, integer divided by 2. That's basically the minimum value, the mid value, right? That's going to be the current guess or potential value for the maximum candies per child. We're simply just computing that mid value here, like we do for all binary search implementations. Now, if we can actually allocate mid candies equally to all of the k children, meaning if this is actually true, but in Python, you don't even need the equal to true. It's actually redundant. You can just go like this to check if it's equal to true. We're actually checking if it's actually possible to distribute mid candies per child equally for all k children using this helper canAllocate function that we defined on line 6. And if it's possible, great. This is our new maximum value. So we'll get the result, update it to now be mid, and then increment or increase our search range values of low to be mid plus 1. Right? Basically, if mid is feasible, we want to update result with a larger mid and then try a potentially larger mid by increasing the low value, right? However, if this isn't the case, if it's not feasible, we have too high of a value, And so we want to decrease or reduce the search space and look for smaller mid-value potential allocations to distribute equally for all k children. So if this is not the case, we'll update high to be min minus 1 for smaller values as the search range. And effectively, once this while loop is done, once low is no longer greater than or equal to high, we've explored all those different possible variations accordingly based on our mid values. We want to return the result because the result would effectively restore or hold the maximum number of candies that can be fairly distributed equally to all k children. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So, on a high-level rundown, how we're really solving this problem. On a high-level rundown, it's really just a binary search implementation. We have a quick base case here, then we have our actual helper method to actually check if we can actually distribute some number of candies mid, and we have for the actual binary search implementation. If a current value is too large, that means that we can't actually accommodate that many number of candies. We have to lower or look for smaller values. If it's too small, great, it's feasible, but let's keep looking for any larger values like the problem asks us to do. Right? So let's go ahead and get into the runtime and memory complexities. For the runtime complexity, it's actually going to be big O of n times log m. N would be the size of the candies, and m would actually be the maximum value in the candies, aka the biggest pile. Why? Because the actual binary search part of this, like the while loop part of this of the implementation, that's going to run in big O of log m. And for each of those steps, we're actually iterating through the candies in big O of n time. And we're doing this when we actually call the can allocate mid, because that's where we actually iterate through all the candies in each call of that can allocate mid helper function. And that's going to be overall time complexity of big O of n times the log of m, or big O of n log m. And for the memory or space complexity, it's actually big O of 1 or constant. We're not actually using any auxiliary memory or any extra data structures. We're only actually using a few integer variables and no extra data structures. We're using a few integers like low, high, and count, and result. And so this is actually a big O of 1 or constant time memory complexity for this solution. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.